value that we got now. So for this case, this is for what? This is for elastic. Okay, so over here, this is for elastic. Up to you. So if you look at the how significant is this value? So if you look at U elastic over U plastic up to a strength of 1.0, right? So this will be equal to 0.765 times 10 to the power of 6, and then the whole thing divided by 1039.972 times 10 to the power of 6. So this will come out to be 0.0, or then I'm going to multiply by 100 to make it in a percent. So this is equal to 0.074%. Okay. So from here, what you realize is the amount, okay, the amount of energy, right? We discovered that the amount of energy, all right, required to induce elastic deformation is relatively small.
Sir,
Yes.
I think you meant to write required to induce.
All right, you're right. Thank you. 1 pint of beer, okay?
Cheers.
Thank you. Okay. Required to small when compared. Hey, wait. It's relatively small when compared to plastic deformation over here of a strain of equal to 1.0. Okay, it's relatively. So when your plastic strain is smaller, yeah, you expect this number to come down. Okay, but it's again the elastic energy is going to be greater than, sorry, the plastic energy required for deformation will still be higher than the elastic. Okay, right. So so for the past 1 hour or so, I've shown you how you can use mechanical properties to decide for what, to decide for costing. So I want to now look at, let's look at the behavior of that equation. Okay, let's look at the behavior, because only if you can understand the behavior of the equation, then you can sketch. Okay, if not, you can't sketch. Okay, you sometimes you are not always in front of an Excel spreadsheet. Okay, so you sometimes you just want to have a feel of the number. What does it actually means? Okay, so again, we are going to look at, okay, the equation that we're going to look at, the strain hardening component. Okay, strain hardening component. So stress PL is equal to A plus by B epsilon PL N. Now this equation over here that we are drawing now is only valid up to its ultimate strength. Okay, you cannot use it beyond its ultimate strength. Okay, so what I mean by ultimate strength is if you have stress, you have strain, right? Then you will have this behavior over here, right? So over here, you know, is your ultimate what strength. So this expression over here is only valid, okay, on this side. Beyond that, is not valid anymore. Okay, that is when necking occur. It's not valid. Okay, so now the first thing we will look at, we're going to look at 3 different materials. Okay, these three different materials. So A1, so material 1, A1 is equal to 300 MPa. All right, and then material number 2, so it's getting to be harder. Okay, and then A3 is equal to 900. I'm at the H MPa. Can you see the MPa? Barely. I'm going to squeeze. Okay, MPa. Okay, and then we're going to have a condition that all three materials have the same P and N. Okay, means the strain hardening coefficient and the strain hardening index are the what? Are the same. Okay, so how this will behave, how this material behave, it will behave like this. Okay, so this is epsilon stress. So this is your 300, 600, 900, 1200, and then 1500. Okay, and then the 300, the first curve, it will behave this way. Right, so over here is A1 is equal to 300 megapascal. And then when when A2 is equal to what? The second material A is 600. Because B and N are the same, it will run parallel. Okay. So A2 is over here is equal to 600 MPa. Right? It's running parallel. And then you have 900. Okay. So A3 is equal to 900 MPa. So this just illustrates to you when B and N are constants, the strain hardening, they're all what? Parallel, right? So over here, this is influenced by your what? By your A value. Okay. Then we're going to draw another set. Okay. So the next set I'm going to draw, again, three different materials. Now A is constant. So i.e., they all have the same what? Hardness. Okay. So the next example we're going to do. Any questions from anyone so far, please? Anyone?
What is the E in Ben?
E in Ben. Where E in Ben?
Means and.
It's and sign.
Ah,
No, not E. It's N. N. It's not E. B and okay, my bad. Okay.
Yeah, that's the and sign. Yeah, it looks like bando, sir.
Okay, B and N. Okay? Not E. Okay.
thank you.
Thank you. Anything not clear, ask now, okay? Don't worry about it. Now the next one, we're going to look at our A constant. So the next one is where you have A1. So again, three different materials. So you have A1 is equal to A2 is equal to A what? A3. Okay. But however, what I'm going to change now is we're going to declare that B1 is greater. Sorry, B1 is smaller than B2. B2 is smaller than B what? 3. And N1 is smaller. So N2 is smaller than N1, and N2 is smaller than what? N3. Right? So we're going to sketch another graph down here. Right? So from here, we have our, I don't need this graph to be so big. Can be smaller a bit. So we can sketch this now. Right? So this is epsilon. This is stress. And all of them will start from A1. Okay, because A1 is going to A2 is going to A3. So the first curve over here, This is your B1, N1, and then the next curve. Now there are no more what? Parallel. B2 and N2. And then finally, this is your B3 and your N3. Okay. Right. So that's how the graph looks like now when A is a constant and then the B is greater. So B3 is greater than B2, B2 is greater than B1, N3 is greater than N2, N2 is greater than N1. So now from here, if we look at the table, okay, if we look at the table that I made you copy earlier, okay. So if we look at the table that I made you copy, so the table that I made you copy, now we're gonna sketch the graph. Again, this is a sketch, right? And then this is epsilon. So this will be 500. This is stress in megapascal, right? 500, 1000, 1500. Then you have 2000, right? So we're going to draw our first material, which is 553. So AISI 1045. Okay, so this is our 553. Okay, so this is our first material. Okay, so this is our AISI 1045. Right? And then we are going to sketch the next one. We're going to sketch our Uzbor. Okay, so Uzbor, it starts from 1040. Okay, so this is 1040. Right? And Uzbor, if you look at the B and N, it's so high, right? So it's very steep. Right? So this is your Uzbor 1500. And then you guys have sketched this before. You guys are very familiar with it. This is our dual phase steel. So our dual phase steel, right? So it's somewhere around here. So you started at 120, right? So dual phase steel will do this. Ooh. So this is our dual phase 600 steel. Okay, and then the last material is our trip steel. Okay, so for our trip steel, right? So we have our trip steel. So our trip steel, we start from what? 412. So our trip steel is our dual phase steel. It's slightly softer, but then it strain hardens like what? It strain hardens like crazy, 0.66. Okay, so this is your 412. Okay, over there is your 412. Then from here, it just went. Okay, so this line over here, this is your TRIP 800. Okay, so that's what I mean by sketch. Okay, so by knowing those constants, okay, you can have a rough sketch how difficult a material is difficult to deform. Okay, any questions so far? No. Okay, so the next case I'm going to talk to you now is design engineer. Don't write down here. So the design engineer, and this is true in real world. Okay, design engineers right, and manufacturing engineers. So manufacturing engineers, they are always going against one another. Okay, I'm going to give you this. This is true everywhere. The design engineer want to use a certain type of material, and the manufacturing engineer say, "No way, Jose." Okay, I'll give you an example. Okay, I'll give you an example. What do I mean by that? And it all, some of you are working in industry or have done co-op, right? And I believe you have seen this. Okay, if your company have a design capability, and a certain engineer say it has to be made of this material, and then as a manufacturing engineer, you just stand out there, and what do you say? No way, right? Always, they are always fighting one another. Am I right? Any of you have done your co-op? Have seen this before? Anyone? that a design engineer always go against the manufacturing engineer? Anyone?
Yep, it's always engineers versus machinists.
Yeah, they never agree. We have to make this of this material. Then as a manufacturer, yep, Sunshine, you can make that material